So I will talk about a joint work with my advisor Nima Anari on a new Plücker relation and its application to the subdeterminant maximization problem. So first, let's see what is the subdeterminant maximization problem. We are given a rectangular matrix A of size m by n, where m is smaller than or equal to n, and a parameter k. We want to compute the maximum absolute determinant on k by k submatrix of A. Note that here we don't restrict ourselves to principal submatrix. So we allow any choice of set I of k rows of A and set j of k columns of A. So our main result is that we can approximate this quantity by a multiplicative factor of k to the O of k in polynomial time. Moreover, our algorithm is very simple, as it is just an implementation of local search. So some background on this problem. The special case when k is the minimum of m and n is equivalent to the lattice volume simplex problem. The lattice volume simplex problem can be roughly described as follows. Given n k-dimensional vectors, select k vectors that span a maximum volume. The volume that a set of vectors span corresponds to its diversity. So, as seen on this slide, V1 and V2 are further apart, i.e. more diverse than V1 and V3. So the set V1 and V2 span a larger volume than V1 and V3. So a diverse subset is also a good representative of the whole set. So finding the most diverse subset is useful for data summary. So this largest volume simplex problem has been studied since the 90s with the first algorithm by Kachizan in 95, giving a k to the O of k approximation factor. In 2015, Nikolov gives a 2 to the O of k approximation for this problem. And this result by Nikolov matches the lower bound given by the Summer et al. In 2014, which says that it is NP hard to get a C to the k approximation for some constant C greater than 1. The main motivation to study the subdeterminant maximization problem in the general case comes from discrepancy theory, namely to compute the determinant lower bound of hereditary discrepancy. The determinant lower bound was introduced by Lovaas et al. In 86, and in 2013, Matusek shows that the determinant lower bound is an approximate upper bound of hereditary discrepancy. So you can see the formulas here. And in this inequality, the left-hand side was proved by Lovaas et al. In 86, and the right-hand side was proved by Matusek in 2013. It is conjectured that the right-hand side can be improved to only O of log n times the determinant lower bound A. If you can do this, and if you can also approximate the determinant lower bound within a constant factor, then you will get an O of log n approximation of hereditary discrepancy. So far, the best approximation for hereditary discrepancy is a log n to the 3/2 by Nikolov and Tangwar in 2014 using a quantity called gamma 2. Gamma 2 cannot achieve a better than a log n to the 3/2 approximation, as noted in a recent paper published in March of this year by Matusek, Nikolov, and Tangwar. In this same paper, they also show that gamma 2 approximates the determinant lower bound within an O of log n factor. Still, the problem of approximate the determinant lower bound within an O of one factor is still open, and it seems that gamma 2 cannot achieve a better approximation ratio than log n. So our result is the first step in a different route to approximate the determinant lower bound. And also the result of Nikolov, Matuset, and Tangwa doesn't directly imply any result on approximate the subdeterminant maximization by a factor dependent only on k. So let's move on to our algorithm for subdeterminant maximization. First, let's consider the k equal to m case. So the algorithm here is a local search. You start with a set S0 of some k columns. At each step, you move to a set T within one neighborhood of S so that it maximizes the absolute value of the submatrix indexed by T. Here T is in the one neighborhood of S. If the size of the symmetric difference of S and T is S mod 2. In other words, T can be obtained from S by removing one column in S and adding one column outside of S. This operation of exchanging one column in S to one column outside of S should remind you of the basic exchange axiom of matrix. So, however, this algorithm doesn't work for the general case. To see why, consider the following diagonal submatrix, the diagonal matrix A. Start from any principal submatrix. If you exchange only one row or one column, you end up with a submatrix with zero determinant. So you need to exchange both rows and columns per iteration. This is a main difference between our work and previous local search algorithm for similar problem. So this idea of exchange both rows and columns is already enough to get a working algorithm for the general case. Here's our implementation of this idea. We have a parameter alpha smaller than 1. Think of alpha as being a constant, maybe 1/2. Start again with a good location S0. That is the tuple of some k rows and some k columns. And what does good mean, I will define later. At each step, consider the local maximum W in the two neighborhoods of S. If moving to W improves the objective by at least 1/alpha, then we move to W and repeat the process, else we terminate and output S. So I will define what does the two neighborhood mean in the next slide. Note that at each step we improve the objective by 1/alpha, so the runtime should be log 1/alpha of the global optimum divided by the value that we start with. So as long as we start with the poly n to the k approximation, our algorithm will run in polynomial time. We know that it is easy to get this poly of n to the k approximation using existing result in the literature. So as promised, let's define the two neighborhood. We introduce a notion of distance. So the distance between two locations S and T, denoted by dst, is half the sum of the symmetric difference between S row and T row and S column and T column. We let the R neighborhood of a location S be the set of all location T such that dst is at most R. We call S a or alpha local maxima if the absolute value of the determinant of A sub S is at least alpha times the absolute value of the determinant of A of sub T for all T in the R neighborhood of S. We observe that per the stopping criteria of our local search, the output S is a 2 alpha local maxima. So let's go back one slide to remind you of the stopping rule, which is here, and let you convince yourself that what I just said was true. So that's the end of our algorithm. Now we go on to analyze the approximation factor. So we will show that this algorithm achieves an approximation factor of k to the O of k. And to do so, we need only to prove this lemma that any 2 alpha local maxima S is a k to the O of k approximate the global optimum. Here we think of alpha as being a constant 1/2 again. So here's the high-level idea of the proof for this lemma. This lemma is a consequence of an approximate exchange property, which I will show in the next slide. And this approximate exchange property is in turn implied by our new Plücker relation. So the approximate exchange property is an inequality between the product of determinant of 2 submatrix indexed by S and T and the product of determinant of submatrix obtained by swapping some rows and columns of S for that of T. So to be more formal, let U row and U column be the set of rows and columns that will be swapped. So here this set EST is the set of all tuple U of U row and U column, satisfying that S delta U and T delta U are valid location pairs. So this simply means that like S row delta U row and S column delta U column both have size K, and the same goes for T. And here we have this restriction on the size of U row and U column. This restriction simply means that we are only allowed to either swap 1 row and 1 column, or as mode 2 row and no column, or as mode 2 columns and no rows. Of course, I didn't write here, but we require that U row and U column cannot be both empty. So let's see an example. In this example, on the left-hand side, the red matrix is A sub S, the blue matrix is A sub T, U column is the empty set, U row is the third and fourth row. On the right-hand side, the red matrix is A sub S delta U, the blue matrix is A sub T delta U. And these matrices are obtained by swapping the third row for the fourth row and vice versa. So now we saw how the exchange property implies the lemma on the approximation ratio. We take the inequality in the exchange property and we substitute S to be the 2 alpha local maxima and T to be an arbitrary location. So per the definition of U, S delta U is in a 2 neighborhood of S. So we can use the definition of 2 alpha local maxima to replace the absolute value of the determinant of A sub S delta U with the absolute value of the determinant of A sub S divided by alpha. Now both sides has an absolute value of A sub S, of determinant of A sub S term which we can remove to obtain this inequality here. So here we just made progress because T delta U is closer to S compared to T. Since T delta U is obtained by swapping things in T for things in S. So next we substitute T to be the global optimum. And we apply the last inequality in the previous slide. So to remind you, this is the inequality that we will apply repeatedly. And we get this chain of inequality here, where T0 is T and Ti is Ti minus 1 delta Ui. Every time we apply this inequality, the distance between Ti and S is reduced by 1 compared to the distance between Ti minus 1 and S. Initially, the distance between T0 and S is as small 2k. After 2k times, the distance between T2k and S is as small 0, so it's 0, and T2k is exactly S. So we get the desired inequality between determinant of A of S and determinant of A of T. So here replace this with A of S. Okay, so now let's see how we get this exchange property from the new Plücker relation. This new Plücker relation is a two-dimensional analog of the classical Plücker relation. So to remind you, the classical Plücker relation involves maximal subdeterminant. So this said that the product of the determinant of two maximal submatrix indexed by column sets S and T can be written as the size sum of the product of determinant of submatrices obtained by switching columns in S for columns in T. Here the delta take value in plus or minus 1. The two-dimensional case is again an algebraic expression, but instead of swapping only columns, it involves terms that swap both rows and columns as seen here. So let's see a visualization of what I just said. In this picture, each term is the product of the determinant of the blue and red submatrix. Here, J is the third column, and I run over the 4th, 5, and 6th column. So I and J are defined here. The two-dimensional case is similar. Again, each term is the product of the determinant of this submatrix in red and in blue. And the first term on the right-hand side is a term where you switch the third column for the fourth column and the third row for the fourth row. So it's somewhat hard to find the formula for this two-dimensional Plücker relation, but once you found this formula, then proving the formula is easy. Just some algebraic manipulation. We note that this Plücker relation, this two-dimensional Plücker relation, is the main technical contribution of our work, and it appears to be novel. And we hope that it will have application beyond our work. So lastly, let's see how the new Plücker relation implies the approximate exchange property. And this is simply a consequence of triangle inequality. Again, let's see the maximal or one-dimensional case first. And we have this formula, and we apply the absolute value on both sides, and we apply triangle inequality on the right hand side. Notice that on the right hand side we have exactly k terms, so here we have a factor k in front. For the two-dimensional case, we have a similar formula. Here, the coefficient C of u is not necessarily only take value in plus or minus 1. But the main thing to remember is that the number of the terms on right hand side is also O of k, and the sum of the absolute value of C of u is bounded by O of k squared. The number of terms on the right hand side is O of k squared, not O of k. So again, apply triangle inequality, you get this inequality where the factor in front is O of k squared. So that concludes our proof for the approximation ratio. So now some open problems. So we have this relatively surprising two-dimensional Plücker relation. This Plücker relation is equivalent to a relation among 2k by 2k fraction of the following skew symmetric matrix X that is obtained by putting A and minus A transpose on the corner and 0 elsewhere. In general, no such Plücker relation holds for general skew symmetric matrix Y, but we can still hope for approximate exchange ACM among 2k by 2k fraction of Y. So I think such an exchange property is probably useful for people who do physics. So of course, it would be very nice to get a 2 to the O of k approximation for the subdeterminant maximization problem, as it will give an O of 1 approximation for the determinant lower bound. Note that local search doesn't get better than a k to the O of k factor approximation. Even when k is equal to the minimum of m and n, and even when we expand the search to C neighborhood for constant C greater than 2, this means that during local search, we allow C exchanges per iteration, or say we allow to search for the local maxima in the C neighborhood. So it seems we need some new ideas. Perhaps we can use the ideas in the Nikolov 15 paper, where he gets the to the O of k approximation for the maximal case. I'll be very happy to discuss more about this if you are interested. And thank you for listening to my talk.